Okay, let's look at this situation here where we have a region defined by x equals y squared and x equals y plus 2, this bounded region. And let's suppose we want to find the area of that bounded region, right? We want to find this area right here. Now, so normally what we do is we think, okay, here's what I'm going to do. I'm going to set up an integral where I have the top function minus the bottom function. Okay, so we look here and we say, okay, I see what's on top here, this thing, and what's on bottom here, this thing. So I'm just going to say integral of this minus this. But let's venture over here a little bit. Now what? Over here. Well, we have this top and we have this bottom. We run into a little bit of a problem here. And look right here. Look what happens here. We have got like, here's the bottom here, and over here's the bottom. In other words, this thing doesn't look like it's really the type of situation we would like to have to integrate with respect to x. So, and you'll notice here that y is not a function of x. See how this right here, it fails the vertical line test. However, x is a function of y. Notice if we go the other way, you can see that every y gives you exactly 1x. So we want to integrate with respect to y. So what does that mean anyway? So let's just think about, remember when we talked about integration initially. When we were introduced to integration, we talked about these rectangles. And we talked about vertical rectangles where we had delta x times, f of x. And we looked at the area of these little rectangles and we added them up. We said, take the limit as the number of those rectangles go to infinity, and we have the definite integral. Well, if we're integrating with respect to y, instead of vertical rectangles, we have these horizontal rectangles. And instead of delta x, we have delta y. See, we have the change in y right here. And here is the height. So we have, let's call this function right here. I'm looking at the area here to the left of this curve, y squared. So what we have is we have delta y g of some y value. So let's see how this looks. If this first rectangle, delta y times g of y1. Okay? That's the area of this y1. Then y2 over here, we have delta y and g of y2. See? G of y2. Calling this function g. Okay? Then we have delta y, g of y3, and delta y, g of y4. And that right there, if that's how we think of the Riemann sum if we're integrating with respect to y. Now, if we add all these up, and we let delta y go to 0, what we get is the definite integral. See? We're going from 0 to 2 g of y dy. Now, let's think about the problem of getting this bounded area right here. Well, first of all, what we need is we need to know the intersection. We need to know, okay, where do these two curves intersect? Well, you can see here and here. And if you look over here, you can see, that looks like y is -1. Remember, we're not talking about what x is. We're talking about what y is. Where do these intersect in terms of y? Well, in terms of x, it's 1, but in terms of y, it's -1. See, right there, -1. And also up here at 2. But let's see how we would proceed. We set these two equal. X equals y squared and x equals y plus 2. So we just set those equal. It's a quadratic equation, so I bring everything on one side. And fortunately, this one factors. And we find that y equals -1 or y equals 2. Now, I've got my bounds of integration, and notice when we're integrating with respect to y, we're not thinking what is the top function and what is the bottom function. We're thinking what is the function to the right and what is the function to the left. And we do right minus left. Because when you think about like this g function right here, getting the area, we're not getting the area below the curve. We're getting the area bounded by the y-axis and the curve. We're getting this over here. So we have to adjust our thinking a little bit. So we take the rightmost function, which is y plus 2, minus the leftmost function, which is y squared, and we integrate, and there's the antiderivative. Using the fundamental theorem of calculus, we get that this area is 27/6, this right here. That's 27/6. And that is the way we approach problems where integrating with respect to x is not so easy, but integrating with respect to y is really just trivial.